This is now the fourth video in Applied Microeconometrics, and today we are going to look at a very important topic. Well, all of my topics are very important, but this topic is very central in econometrics because of the fact that today we're going to talk about endogeneity. In that sense, it's important to, remember that what we have done so far is that we have been looking at, quantum regression models and distribution regression models. And both of these models are very well suited models at the moment that we have impact heterogeneity. At that moment in time, if we have impact heterogeneity, it is not good to use ordinary squares or other kind of linear models, but then you should actually use non-separable models like distribution regression as well as quantum regression. So that's what we have done so far. But we haven't talked yet about the problem of endogeneity, and we should take into account that at the moment that we have endogenous regressors, we should still take that into account at the moment that we have we're going to use quantile distribution regression. It's not like that you can say like, well, quantile and distribution regression already take that into account, or the fact that in quantile or distribution regression we do not have endogeneity problems. Actually, also in quantile and distribution regression we do have endogeneity problems, and we do actually have to take them into account. So therefore today we're going to look at what to do at the moment that we have endogenous regressors. For that I'm going to have the following model. We now have a model with two equations. The first equation is usually called the outcome equation, and it has a yi at the left hand side, and we have beta 0 ui plus beta 1 ui times xi plus beta 2 ui times di at the right hand side. We have a second equation that is usually called the endogenous variable equation, and it has a di at the left hand side, and then at the right hand side we have gamma 0 vi plus gamma 1 vi xi plus gamma 2 vi times zi. Well, this is now two equations, and we see that immediately that the di that we have over here plays a very important role. The reason behind that is because of the fact that here it is a right-hand side variable, and here it actually enters the left-hand side. So it enters twice in our model, once at the right-hand side and once at the left-hand side. In addition to that, what we can say about this model that we have over here is that both equations are, random coefficients models. This is a random coefficient model, and this is a random coefficients model. Well, in order to give you some idea of, what we could do in this particular case, it's always good to think of an example. And the example that we're going to have is now again exactly the same as the example that I already have given you a couple of times before. And that is that we're going to look here at the relationship between log hourly wages and the, say, education level of individuals. So that means that yi is going to be the log hourly wages, xi are all kinds of human capital characteristics, including, gender, ethnic background, age, and the like. Region is also another one. And then, di is going to be the level of education. So di is in this case education. Now so far what I usually did, and I did that because of the fact that I wanted to make the things as simple as possible, is that I always represented education by a college dummy. It's better now in this case to think about something else. The reason behind that is because of the fact that I now need a continuous outcome variable, because of the fact that di enters here at the left hand side, and therefore I want to have di to be continuous, and therefore in this particular case it's better to think of di to be, for example, the number of years of schooling that you have. Zi is going to be an instrument, and in the literature on the returns to education there have been many different instruments, but one instrument that has received at least a lot of attention is the one by Engrist and Kruger, published in the Quarterly Journal in 1991, and they look actually at the quarter of birth within a particular year. Or maybe you have heard about this paper before. If you haven't, that's not a problem right now because of the fact that I'm going to discuss that at the end of this video. But well, for now it is sufficient to think about Zi to be an instrument. And later on I'm actually going to say what that actually means, that Zi is an instrument. In addition to the observed characteristics x, d, and z, as well as the outcome variable y that we have over here, we should realize that we also have unobserved characteristics. We have here ui. Ui is going to be all those unobserved characteristics that are going to have an impact on yi. And we have vi, and vi are going to be all the kinds of characteristics that are going to have an impact on this di that we have over here. In our particular example, we can think of ui to be, well, apart from the fact that it might be market luck, just the fact that you sometimes get a very nice job that pays very, very well, we can mainly think of ui to be talents. Talents that are going to help you to get a higher wage. What can we think about? Well, for example, intelligence or smartness. Most employers like intelligent employees, so therefore intelligent employees, at least for a particular kind of jobs, are going to be much better paid than not that smart individuals. You can also think of communication skills and all kinds of other skills that are going to help you to get better wages. Well, apart from UI, we also have VI, and VI can now be seen as academic ability. All those kind of talents that are going to help you in school. Question again arises, what might that be? Well, this may also be intelligence. I do think that it helps at the moment that you're intelligent to, well, receive a higher level of schooling. Also here we could think about communication skills for some, well, kind of schools, but also for some kind of topics that you're going to get into school. You should realize that it might be good to have good communication skills. We can think of here again of all kinds of other skills that are going to have an impact on this D that we have over here. Remember that when I said that when I was discussing for the first time the random coefficients model, then I said that ui that we have over here is typically going to be assumed to be, well, uniformly distributed. I'm going to also here make that assumption for ui, and I'm also going to make exactly the same assumption for vi. However, I'm going to allow for the fact that ui and vi, they may be correlated with each other. And that's very likely to be the case in our particular example. Because remember, ui was, well, all kinds of talents that are going to have an impact on the wage. Vi were all kinds of talents that are going to have an impact on this di that we have over here. And I said that, for example, smart as being an intelligent individual helps you at school, but also helps you directly at the labor market. So that implies that U and V, they are likely to be correlated to each other. And that's bad news. And the reason behind that is because of the fact that that implies that if U and V are going to be correlated with each other, well, we do of course know that D and V, they are also correlated to each other. And that's for the simple reason that V here is at the right hand side of the D equation that we have over here. But if U and V are correlated and D and V are also correlated, that means of course that V has an impact on both U as well as D, then it's very likely to be the case that U and D, they are also correlated to each other. And that's bad news. That means of course that we can no longer do quantile regression. Well, you actually know that for standard ordinary squares, that if the error term is correlated with any of the regresses, that will give us inconsistent estimators. But exactly the same problem we have at the moment that we're going to look at quantile regression. In that sense, essentially, quantile regression is not that different from, say, standard mean regression. Because the question arises, what is actually quantile regression doing? Well, suppose that we're going to do median regression and we would like to look at the impact of this di that we have over here. What do we then usually do? Well, then what we're going to do is that we're going to look at different, say, values of this di that we have over here. So we could, for example, look at a very high level of di and a very low level of di. And then what we're going to do, for example, at the moment that we're going to look at median regression, is that we're going to look at the median for the high level of DI and the median of the low level of DI. And if this, well, the first median is larger than the second median, then we do of course know that the impact is going to be positive. That means that in that particular case, what is the impact of, say, D on yi? That is of course represented by this beta 2. At the moment that we're going to look at median regression, it's the beta 2 evaluated in half that we're going to look at. And based on that, we can actually determine that beta 2, at the moment that the median for high levels of DI is larger than the median for low levels of DI, that beta 2 must be positive. And if the difference is large, then beta 2 is also large. If the difference is small, well, then that means of course that also beta 2 is going to be small. If it's going to be negative, then at that moment in time, beta 2 is going to be negative. But that we can only do at the moment that D and U, they are not correlated to each other. However, in this case, we do know that D and U may be correlated to each other. Well, that is bad news for the simple reason that we should realize that then, well, we do know that, of course, D is affected by V. Let's assume that it is positively affected by V, so that means high levels of D come together with high levels of V. What does that mean? Well, that means that at the moment I'm going to look at a high level of D, well, then I do know that on average at least, individuals that have a high level of D also have a high level of V. But if there is also, for example, a positive correlation between U and V, then these individuals also have a high level of U. And that means that if I'm going to make a comparison between high levels of D and low levels of D, then I do not only make a comparison in terms of the D's that we have over here, but I also make a comparison in terms of the U's. I know that then, on average, the individuals with a high level of D are going to have a higher level of U than the individuals that have a low level of D. And that is actually, then it makes it actually difficult, because that means, of course, that at the moment I'm going to make these comparisons, as I said before, I'm going to compare the mean of a high level of D with the mean of a low level of D, then I do no longer know whether, say, the increase in this case of the median is due to the increase in D, or whether it's related to the change or the increase in the U that we have over here. Also here it's good to look at the example that we had before. We do of course know that at the moment that we're going to look at differences in education level, so suppose that we're going to make a comparison to a high educated person with a low educated person. Well, then what we know of course is that high educated persons usually have a higher level of intelligence, a higher level of V and U than, say, low educated individuals. That means that at the moment I'm going to make a comparison in terms of the medians, well then I do not know whether the median among the high educated is higher just because of the fact that they have higher levels of education, or whether it's also related to the fact that they also have a higher level of intelligence. Still, we would like to estimate beta 0, beta 1 and beta 2, so that cannot be done now by, say, standard quantitative regression. We have to think about something else. But before I'm going to say what else we're going to do, that's actually the control function approach. Before I'm going to do that, the first thing that I'm going to do is that I'm going to make a couple of assumptions. The first assumption I'm going to make is that U and V, they are going to be independent from X and Z. What does that mean in terms of this model that we have over here? Well, first of all, Z is going to be then independent from, say, U as well as of V. That means that Z is going to be, well, you could say, an exogenous instrument. Notice that this is actually stronger than we usually have in standard linear regression models, because of the fact that in standard linear regression models we only assume that the U and the V are going to be, well, uncorrelated with X and Z, but now in this case I'm going to assume independence, and the reason behind that is because of the fact that well, uncorrelated in this case is not enough at the moment that we have a non-separable model. So that's the first assumption that we're going to make. Actually, we make exactly the same assumption at the moment that we're going to look at X. So actually, X can also be seen here as an exogenous instrument, It is actually an exogenous instrument, but it's not an exclusion restriction. The reason behind that is because of the fact that x also enters here at the right hand side in the first equation, and therefore here it's simply a control variable. A control variable here in this very first regression. So therefore x is an instrument, can be seen as an instrument, but it's not an exclusion restriction because that is only z. Then in addition to that, what we're going to assume here is that v is going to be continuously distributed. Well, that's actually something that we already did because of the fact that we already know, because of the fact that we, well, know that vi is uniformly distributed. But in addition to that, I'm going to use some notation. I'm going to note the function h, x, z, and v. Well, that's actually nothing else as the right-hand side of the second equation that we have over here. So gamma 0v plus gamma 1v times x plus gamma 2v times z. Well, this equation that we have for particular outcomes of x, z, and v, well, I'm going to assume that this function is going to be strictly increasing in v. So that means nothing else is whatever gamma 0, gamma 1, and gamma 2 are, well, at the moment that I'm going to increase v at this right-hand side, then this whole right-hand side should actually increase. These are the two assumptions that I'm going to make. So that actually implies nothing else is that at the moment I'm going to increase v. So at the moment that somebody, for example, becomes smarter, has more intelligence, then d should increase. So then schooling, in fact, should increase. But as I already said, what we're going to do is that we're going to look at the so-called control function approach. And I'm not that sure whether you have ever heard about the control function approach before. So therefore, the first thing I'm going to do over here is that I'm going to introduce the control function approach. I'm not going to do that, say, based on the model that we have so far. What I'm going to do is that I'm going to, well, make you explain the control function approach based on another kind of model, and that's the, well, linear regression model. That's a model that you have already seen many, many times before, and that's actually what I'm going to do right now. In order to explain what the control function approach is that it can be seen as an alternative to IV estimation. IV estimation, well, that is something that you have already heard about many, many times before. IV estimation is, I would say, a very general method to take endogeneity into account, to take into account that you have an endogenous regressor. It's an estimation method that makes it possible to still consistently estimate our beta coefficients in the case that we have an endogenous regressor. Now you might of course know already that endogeneity can be taken into account also in other ways, such as for example fixed effects. But for fixed effects you need a panel data model, and therefore you can say that, well, IV estimation is, well, so far the only method that you have seen that can very generally take endogeneity into account. Well, but there are alternatives, and one of these alternatives is the so-called control function approach. Well, in order to explain the control function approach, let's look at a very simple model. In this case, we have yi at the left-hand side, and we have now beta 0 plus xi beta 1 plus di beta 2 plus ui at the right-hand side. And then the second equation that we're going to have is that di is at the left-hand side, and now we have gamma 0 plus gamma 1 times xi plus gamma 2 times zi plus vi at the right-hand side. Again, we have two equations over here, and again, di enters, well, twice here and over there. You could actually say that this is almost identical to the model that we had 2 slides back, with the only difference that we now have here linear regression and linear regression model. So we have linear regression as, well, equations, whereas earlier we had quantum regression, or you could say random coefficients models. I'm going to make a couple of different assumptions with respect to this model that over here. We're going to assume that x, d, z, and u, as well as vi, they're going to be IID. In addition to that, I'm going to make a couple of assumptions. I'm going to assume that, well, z is going to be uncorrelated with v. X is actually going to be uncorrelated with v. But z and x are also going to be uncorrelated with the u that we have over there. So in that sense, again, z is going to be a good instrument, and x is going to be an exogenous regressor either here or a good instrument at the moment that we're going to think about it here in this second equation. However, again, we are going to allow for the fact that u and v, they're going to be correlated to each other. And again, that is bad news because of the fact that if u and v are correlated, well, given the fact that di actually is affected by v as well, it means that both u and v, they are going to be affected, both u and d, they are going to be affected by the same v that we have over here, and therefore it's very likely to be the case that d and u, they're also going to be correlated with each other. And that's bad news because of the fact that that means that it's going to be impossible to estimate this equation with respect to ordinary squares. Gives you biased and inconsistent estimators. So therefore what we then typically do is that we're going to use IV. We're going to use IV instead of ordinary squares in order to estimate this thing that we have over here. But there is an alternative, as already said, and that is the control function approach. In order to introduce the control function approach, let's assume that we have an additional relationship, and that's a relationship with respect to ui and vi. We have here that ui is equal to rho vi plus ri. Well, what we see now, first of all, is that, well, this first term shows the relationship between v and u, even though this is already quite, well, you could actually say quite general. What we could have done is that we could have made it more general by including, for example, higher order terms. Thus, the relationship does not have to be linear as we have over here, but we actually want to keep it as simple as possible, and that's the reason why I simply have here a linear relationship. But we could have looked at the higher order terms as well. Well, and then in addition to that, we have this r. Well, we're going to assume that r is going to be uncorrelated with v, but also actually with x and with d. And that means essentially that this ri that we have over here can be seen as a perfect, say, completely random variable. It's not going to be correlated with anything, so that's not really going to be a problem. We see this relationship over here, then what we could actually do is now substitute this into there in order to get the last equation that we have over here. Well, we should realize that this last equation can be seen as a fantastic equation, and the reason behind that is because of the fact that it immediately says that at the moment that we can run a, say, regression where we have yi the left hand side and we're going to regress it on x, d and on v, well, given the fact that r is not correlated with any of these variables that we have over here, it means that we are going to get unbiased and consistent estimators of beta 0, beta 1, beta 2 and this row that we have over here. We even get it for the row that we have over here. Well, that is of course very nice. However, there is one practical problem with respect to this regression equation, and that is that you should realize we can actually not run this regression equation. And the reason behind that is because of the fact that we should realize that vi is by definition unobserved. It's the unobserved part in this second regression equation that we have over here. So therefore we can actually not run a regression of yi on xi and di as well as vi. And therefore what we do usually instead is that we are going to run a regression of yi only on x, I and di. That's what we typically do in ordinary squares. But that immediately implies, of course, that because of the fact that then the remaining error term is going to be this thing that we have over here, well, that immediately implies, of course, that we're going to have troubles because of the fact that that makes di, which actually also depends on v, directly correlated to the error term that we have over here. So that's in a nutshell the problem, of course, that we have. One nice thing what we see here as well is that in this context, well, any kind of endogeneity problem can be seen as an omitted variable problem. The reason why we have an endogeneity problem in this particular case is because of the fact that we omit, in fact, this regressor of the unobserved term vi well, we actually omit this regressor from the equation that we have over here. Would we have included it, then we would not have had any problems, but because of the fact that we omit it, we are going to have this omitted variable bias. Remember that when you were discussed for the very first time IV, well, that's probably either in the first year with Annika or later with Aga, then what you're going to, well, then you hopefully remember that one of the problems that why you have an endogeneity bias is because of the fact that there might be an omitted variable bias. Well, this context actually says that, well, essentially any kind of endogeneity bias can be seen, or endogeneity problem can be seen as an omitted variable problem. Well, we are later on going to see that we can actually, this ID that we have over here is still very important to find a solution. But before I'm going to do that, let me first define a control function. A control function W is a random variable with a characteristic that, well, first of all, the mean of u conditional on dx and w is going to be exactly equal to the mean of u conditional on only x and w. That's what a control function is. Well, in words, this says actually nothing else is that we do, of course, already know that u and d, they are correlated to each other. That's what I said on the previous slide. And we even know that u and d, they are correlated to each other, even in the case that I control for this x that we have over here. We should realize that that's usually what we do in multivariate regression analysis. If we do univariate regression analysis, in this case on y on d, then it's going to be very likely to be the case that the remaining error term that we're going to get is still going to be correlated, say, with our, in this case, the d that we have. But therefore, what we typically do is that we control for additional, say, observed characteristics, these x's that we have over here, in order to make the remaining, say, error term that we have to be at least uncorrelated with the u that we have over there. But actually, we also know that that's not the case in our particular situation. We know that even in the case that we control for x, then still u and d, they are going to be correlated. But what this characteristic actually says is that at the moment that we also are going to, say, control on w, on our control function, well, then we are going to see that if we also take into account this w, well, then actually we can get rid of this d that over here, which means nothing else that if we also correct for w, for the value of w, then u and d, they are going to be uncorrelated with each other. Well, that means essentially nothing else as that w actually essentially contains all the information that makes this d to be correlated with that u that we have over there. It has all the, say, endogenous information that is necessary for essentially the correlation between d and u. And if we correct for that, then actually we have already taken all that information into account, and then actually u and d are going to be uncorrelated. At the moment that we're going to look at this regression equation, then we get already a suggestion with respect to a potential control variable. And the potential control variable that we're going to have is this v that we have over here, because of the fact that we do already know that if we not only, say, control for the axis in this regression, but also correct for v, well, then we do see that the remaining error term that we're going to get is going to become, well, uncorrelated with the d that we have over here. So therefore, at least in this sloppy way, we do already know that potentially this v that we have over here is going to be a good control function. But the question arises, how can we actually prove that that is true? Well, we can do that by, well, essentially trying to replace in this definition that we have over here the role that w has by the v that we have over here. So the only thing that I need to do is that I have to replace here at the left hand side w of v, and then I have to prove that this actually holds for the case of v. How can I do that? Well, if I would like to write this out, then the first thing I can do is that I can now also condition on the z that we have over here. That is allowed, of course, because of the fact that we do know that z is, well, uncorrelated with u. So therefore we can always condition on it. If you don't believe me, well, then just do it the other way around. At the moment that we have that z is uncorrelated with u, then we do, of course, know that we can actually get rid of it and come back to that thing that we have over there. So this actually is going to be true. Then the next thing they can do is that they can now use the definition of di that was equal to di is gamma 0 plus gamma 1xi plus gamma 2zi plus vi, so I can actually write it now like this. And then the next trick that I'm going to have is that I can actually now use the fact that this xi that is over here is exactly the same as that xi that is over there. That one is equal to little x, so this thing becomes also equal to little x. Take into account that this is actually something essential, even though this seems to make sense and it seems to actually not make a big difference if I write here a small x instead of a large x. Actually, it is a big difference. And the reason behind that is because of the fact that we should realize that a large x is stochastic, so it can actually be anything. We do not beforehand know what it actually is. But here we actually condition on the fact that we are only going to look at xi equal to little x. Little x could be, for example, large x could be gender, and little x could be now the case in which we're only going to focus on women. Or xi could be a certain range of ages that people can actually have, or a particular kind of region. Well, whatever it is, what we're going to do is that we're going to, well, base ourselves on a subsample for which xi is always equal to this little x over here. So for example, only to women, and that means that if we know that already over here, that we have been looking only at the subsample for which xi is equal to x, well then we can also use that over here. So we can write this as a little x, but we can exactly do the same for z because of the fact that we also know that z is equal to this little z over here. So therefore we can write it like this. And then finally we can even do it for the vi that we have here, because we even see that vi, for whatever it is, it must be equal to this little v that we have over there. Well, and then we are going to get to the most important step, and that is that we should realize now that this thing that we have over here, this restriction that we have over here, is completely deterministic. There are no, say, capitals here anymore, and that means that this thing now becomes completely deterministic. What does that mean? Well, that means that we do not have to, well, condition on it anymore. And the reason behind that is because of the fact that no random variable can ever be, well, correlated with a deterministic variable, to something which is deterministic. If you do not believe me that that is actually true, then ask yourself what is going to happen at the moment that u is actually correlated to something which is deterministic. Well, correlation is always mutual, so that means that if u is correlated with something which is deterministic, well then it should also be the other way around. The deterministic variable should then be correlated with u. But how can something which is deterministic, which never changes, which always is given, to be correlated with something else? Because correlation means that if that something else is going to change, well then this deterministic thing should change as well, but deterministic things actually do not change at all. So there we should realize that we can actually get rid of this restriction over here because of the fact that u is not going to be, well, correlated to this restriction that we have over here. And now we're almost done. Now we should realize that we can another time take out now zi over here because of the fact that, again, z is uncorrelated with u. And now actually we do see that we can actually write this statement over here where, well, simply vi, well, replaces the role of wi, and that means, of course, that vi is a good control function. Well, we actually already knew that because of the fact that I already said that at the moment that we control for vi, then we do know that di and the remaining error term is going to be uncorrelated. But we do already know as well that this regression equation that we have over here doesn't work for the simple reason that vi is unobserved. So the question arises, what can we do about that? Well, vi is of course unobserved. It's by definition the unobserved part that we have over here. But one thing that we could do is that we can try to estimate it. Instead of knowing it, we can try to estimate it. And that's actually not that difficult because of the fact that we have this second regression equation over here. What I can do is that I can bring all these terms to the left-hand side and write the other way around to see that what we in the end are going to get is Vi is equal to Di minus gamma 0 minus gamma 1 xi minus gamma 2 zi. And that means, of course, that if I know d, x, and z, and I also know gamma 0, gamma 1, and gamma 2, well, then I can actually, based on the, say, observations of d, x, and z, I can also calculate the VIs. Then I would actually be able to observe the VIs. But the problem, of course, is not so much that we do not observe di, xi, and z, but the problem is that we do not know the gamma 0, gamma 1, and gamma 2. They are unknown coefficients to us. But of course, we can try to estimate these. Gamma 0, gamma 1, and gamma 2 can actually be estimated by a first stage regression of di on xi and zi. Given the fact that we do know that Vi is uncorrelated with x and z, well, we can simply run here a regression of dx and of d on x and z and get, say, consistent and unbiased estimators of gamma 0, gamma 1, and gamma 2. But that, of course, implies that we can also get a consistent and unbiased estimator of Vi hat. What we can simply do is substitute here, in here, well, gamma 0 hat, gamma 1 hat, and gamma 2 hat. Then what we can do is that we can then rewrite our regression equation a little bit. The regression equation that we had so far, y on x, d, and rho, v, of course. What we can now do is that we can, well, rewrite this a little bit. What we can do is that we can now add and subtract, well, rho times Vi hat, and then we get this thing over here. Well, we can rewrite this a little bit. The first thing we can do is that we can bring this to the forefront, then we are going to place it over here, and if we then are going to take the Vi and Vi hat together, then we're going to get these, well, two terms over here. If we then are going to write this as Ri star is rho Vi minus Vi hat plus Ri, well, then what we're going to get is now this regression equation that we have over here. And this is another regression equation that is actually, well, it is feasible because of the fact that now what we have is a regression equation of yi on xi, di, and Vi hat. Well, that is feasible. However, there is still one problem, and that is that, well, we are going to see that Vi hat is actually not uncorrelated with the Ri star that we have over here. And the reason behind that is because of the fact that in the definition of Ri star, we actually have Vi hat. Vi hat is actually over here, and therefore Vi hat cannot be, say, uncorrelated with itself, and therefore also not be uncorrelated with Ri star. So at the moment that we're going to run this regression, we know for sure that it will give us, well, biased estimators. There's still a bias in here. Now you might of course say like, well, then we actually haven't gained anything. That's not completely true. We should realize that there is still one nice thing, and that is that we know, of course, that actually gamma 1 hat, gamma 2 hat, and gamma 3 hat, they're going to converge in probability to gamma 1, gamma 2, and this gamma 3 that we have over here. And that means actually nothing else, going back to the previous slide, that even though Vi hat and Vi, they're generally different from each other because of the fact that Vi hat is an estimator. It depends actually on the data set that we have, and therefore generally will not be exactly equal to Vi. But at the moment that n goes to infinity, well, then these things become exactly identical to these three things that we've over here, which means, of course, that Vi hat is going to converge to Vi. So Vi hat is a consistent estimator of Vi, and that means that if n goes to infinity, then this part that is over here is going to completely drop out. That means, of course, nothing else is that, well, even though for, say, any finite sample, so for any finite n, this is going to give us a bias, this regression is going to give us a bias, but at the moment that n goes to infinity, well, then we actually have exactly the same regression as the regression that we had 2 slides back, And that means, of course, that the bias actually will reduce to 0 if n goes to infinity. But that means, of course, that what we're going to get is that even though we have a, say, biased estimator, we have well, asymptotically unbiased estimator. Well, asymptotically unbiased means actually nothing else as that we are going to have a consistent estimator. At least under very general conditions, asymptotically unbiasedness means consistency. Well, that means now that we have a, say, consistent but unfortunately biased estimator. Now you might of course say like, well, but then maybe it would be better to use IV because of the fact that we have an alternative that can also take endogeneity into account, and that is IV. But we should realize that IV actually is also a biased estimator. I hope that, well, you know that from, say, your earlier classes, that IV actually is also a biased but consistent estimator. So that means that we now have two estimation techniques. Both are actually biased, but both of them are also consistent. So both methods actually are very good at the moment that we have many observations. Not that great if we have very few observations. Now you might of course say like, well, but then generally what we can do at the moment that we have an endogeneity problem is that we can do both of them. We could do, say, IV, and we could do the control function approach. And well, depending on the result that we can actually choose one of the two. Well, now we should realize that actually, even though I have been talking a lot about the control function approach and as essentially an alternative to IV, you should realize that at least in a linear model, we should realize that the control function approach as well as IV, they are, you could say, numerically identical to each other. What does that mean? Well, that means actually that at the moment that you're going to do IV, and then after that you're going to do the control function approach, you're going to use this first stage, the second stage regression of the control function approach and IV. By the way, before going on, we do of course also know that, well, in a first stage of IV, we actually are going to do exactly the same thing as what we do here in the control function approach. But if you're going to do that, both for IV as well as for, say, the control function approach, then your final beta coefficients will be exactly identical. They will need not be more or less identical, but they will be exactly identical. So now you can of course ask yourself the question, why do we actually discuss the control function approach if it gives us exactly the same results? Well, the answer to that's actually only true in the linear case. In a non-linear model, generally the control function approach and IV is going to be different. And that's something that we are going to see as well at the moment that we're going to look at quantile regression analysis. If you would like to know a little bit more about non-linear models and the control function approach, well, then what you could do is to go to the NBER Summer School of Immons and Wooldridge. Well, it is nowadays already quite old, but as far as I know, it's still possible to find this at the web. It's chapter number 6 is about the control function approach. Well, and then before I'm actually going on, or going back in fact to the model that we had before, I would like to say one final thing about the control function approach in comparison to IV. What we should realize is that, well, the control function approach and IV, they are, you could say, almost opposing methods, approaches to take endogeneity into account. We do already know that endogeneity, of course, means that D and U, they are correlated to each other. So therefore, generally what you can say is that at the moment that you would like to do something about that, then you either have to do something with respect to D, or you have to do something with U in order to make D and U no longer to be correlated to each other. That's essentially what you have to do at the moment that you would like to, say, consistently estimate the beta 2 coefficient. Well, IV actually does the approach of looking at di, at the regressor. What IV in fact does is that it, instead of running a regression of y on x and d, which will give you inconsistent estimators of this beta 0, beta 1, and beta 2, instead what it does is that it's actually going to look at an alternative regression. It's going to look at an alternative regression of y on x and on a, say, well, average or mean value, a conditional mean of d, conditional on the outcomes of z. That is what IV does. Well, even though that actually works in the end, and you can show that it works, it's pretty hard to understand that. Why would you actually want to run a regression, a different regression, than the regression that you actually have over here? The control function approach does something different. It actually says like, well, if D and U are correlated to each other, it's better to do something about the error term, about the unobserved part. It's better to, well, actually change the error term in such a way that the error term, the remaining error term, is no longer going to be correlated. It's exactly what you do here. You include an additional variable in such a way that R, the new, say, error term, is no longer going to be correlated with the D. Well, in my opinion, that makes much more sense. It's much more intuitive. In that sense, it's a little bit surprising that at the moment that you're going to look at the IV and the control function approach, IV is actually quite old. The first applications with respect to IV, I'm not exactly sure, but are almost 100 years old. At the moment that you're going to look at the control function approach, well, that's actually much newer. I'm not exactly sure when the first control function approach application arrived, but I think that that was around the turn of the century. So that's only 20, 25 years old. That's a little bit surprising given the fact that, in my opinion, the control function approach, it's much more intuitive. I would like now to go on with the original model that we started with. Remember that we were actually not that much interested in looking another time at the linear regression model, but instead we wanted to look at this model that we have over here. It had two equations, well, also here an outcome equation and an endogenous regressor equation, but instead of having, say, two linear regression models, we have here two random coefficients models. Here the random coefficients model for the first equation and here for the second equation. Apart from that, we have made a couple of assumptions. First of all, we have assumed that u and v are independent from x and z, and we have defined this function hxzv, which was actually nothing else as the right-hand side over here. But what was also assumed was that this function that we have over here is whatever the right-hand side is going to be, it's increasing with respect to this v that we have over there. So that was actually the model that we have looked at so far, and now the question arises, what is going to be, how can we actually estimate it? The answer to that is, again, the control function approach, but then of course the question arises, what is our control function that we're going to use? Well, that's actually in this case W1. W1 is, well, just the definition of a control function. We usually denote it by W1, but in this case it is going to be defined as being the distribution function, well, of D1 conditional on X1 and Z1, but actually also evaluated in D1 conditional on X1 and Z1. Well, take into account that this actually nothing else is the distribution function of, well, the endogenous regressor based on, say, the exogenous regressor as well as the instrument. And another thing that we take into account is that this, well, this function that we have over here is actually random. And that's not because of the fact that this distribution function is random, because of the fact that distribution functions generally are not random, but it is because of the fact that D1, X1 and Z1 are random. And we know already for a long period of time that at the moment that we're going to evaluate a function in a random variable, then we also get a random variable. Now that means that this thing that we have here at the right hand side is a random variable. Also means, of course, that W1 is a random variable. And now we are going to state that this is a good control function. However, before we can say anything sensible about that, what we need to know is what is actually a good control function in this particular context, in the context of this particular model. Well, the idea behind the good control function is that it must be, say, a random variable in such a way that at the moment that we're going to look at u1, it must be independent from d1 condition on w1 and x1. That is a good control function. That's the definition here of a good control function. Take into account that is almost identical to what we had in the linear regression case, with the only difference that in the linear regression case we only needed that it was uncorrelated. So instead of having no correlation, we now need independence. And you might already have recognized that in non-separable models we usually need independence, where in, say, standard linear regression models we only need non-correlation. What does this mean in words? Well, this means in words that we have already seen that u1 is actually dependent on d1. So we do not have independence between u1 and d1, even in the case that we're going to condition on the regresses on this x1 that we have over here. But now what we have to, what we actually state is that, u1 is going to be independent from d1 at the moment that, apart from conditioning on x1, we also condition on the control function, this w1 that we have over here. Well, the proof of all of this is in a paper published by Embens and Newey, published in Econometrica in the year 2009. And it's based on two observations, where actually the first observation is maybe the most important one to understand. And that is that conditioning on W1 is the same as conditioning on V1. That actually means that if we would like to condition on V1, then apart from using V1, we could actually also use this W1 that we have over here. And actually we should realize that conditioning on V1 is very, very useful. Why? Well, at the moment that we are going to condition on V1, then we immediately solve the endogeneity problem. In order to understand that, it is best another time to go back to this, say, slide that we have over here. Remember that the main problem that we had in order to estimate this regression equation that we have over here with respect to standard quantum regression analysis is that there is correlation or dependence between ui and di. And this dependence, of course, goes through the vi that we have over here. Because of the fact that u and v, they are correlated to each other. And because of the fact that we also know that d and v are correlated to each other, simply because of the fact that v enters into the equation of d, well, therefore we do know that u and d, they should also be correlated to each other. And we do already know that that actually gives us problems with respect to quantum regression analysis, because of the fact that if we would like to compare two different levels with respect to d, say a high level of d and a low level of d, well, then we should realize that if, for example, the quantiles are also in such a way that the quantile for a high level of d is higher than the quantile for a low level of d, then we do actually not know whether that really comes from d or from ui. So whether there's really an impact from d, which should of course belong to the beta 2 that we have over here, the estimated beta 2, or that it actually comes from ui, and then it can actually, well, affect yi through all the channels that we have over here, beta 0, beta 1, as well as the beta 2 that we have over here. That is the main problem that we are going to have at the moment that we have a correlation between ui and di. But now let's assume that we actually can condition on vi. That means actually nothing else is that, in layman terms, what we could do is that we could look at our population and we could look at the subpopulation for which vi has a particular number. Say, for example, we fix on the subpopulation for which vi is exactly equal to half. That's of course possible. Well, then what we can do is, based on this, we can still look at the differences in di in this particular subpopulation for which vi is equal to half. Question, of course, arises, how is it possible that there are still going to be differences in di if we fix the level of vi? Well, that's possible because of the fact that we should realize that, well, it is not only vi that has an impact on di, there are also other things, such as xi, that we already control for over here, but also zi. So we should realize that at the moment that we're going to look at the, say, variation in terms of di, if we fix vi and we correct actually, or we control even for xi, well, then the variation in di is completely determined by the exogenous zi that we have over here. And then it implies that at the moment that we're going to fix vi, as well as that we control for xi, that at the moment that we're going to look at different values with respect to di, well, then we know that vi is exactly identical in both cases. What can we say then about u? Well, then, of course, the, say, u's are also on average going to be exactly the same. Why would it be the case that for the same level of v, we are going to have different levels of u for, say, a high level of d or a low level of d? Because of the fact that the only reason why d and u are going to be correlated was because of the fact that high levels of d generally had also, say, well, relatively high levels of v. But that's no longer the case. So therefore, now at this moment in time, we do know that at the moment that we're going to condition on v, well, then we also know that the, say, average outcomes that we are going to have with respect to u, they are no longer, or u is no longer going to be correlated with this d that we have over here. So we don't have to be, well, afraid anymore that at the moment that we're going to compare a high level of d with a low level of d, that the u's actually may differ, because of the fact that we do know that the only way in which the u's could have been different is through the channel that we had with respect to v, but we have now fixed the levels of v. Well, this is really important, and well, that's actually the most important step that we actually have to take with respect to what we have to prove over here. Then the second thing that we have over here, well, before I actually go on with respect to that, the problem, of course, that we have, as in the linear regression model, is that phi is actually not observed. So that's the only problem that we have. It would be nice, of course, if we could observe phi1, and then we could simply say, like, well, we're only going to look in our data set to individuals with particular levels of v1, as we also did essentially with respect to the linear regression model. But the problem, of course, is that phi1 is not observed. But the nice thing is that this actually says that we can instead use w1. We can use w1 instead of v1 in order to condition on phi1. Because at the next slide we will actually prove that w1 and v1 are exactly identical to each other. So that it actually would be possible. Well, the problem, of course, is that w1 by itself is also not observed. And that's not because of the fact that we do not observe d1, x1, and z1, because of the fact that d1, x1, and z1 are actually observed in our data set. But it has more to do with the distribution that we have over here, the distribution of d1 conditional x1 and z1, that we actually do not know. That's a population distribution, and population distributions are not known for us as econometricians. But we should take into account that we could try to estimate this distribution that we have over here in order to at least get an estimator of that thing that we have over there. But then still what we actually have to prove is essentially what I said after that. What I said after that was that, well, if we can condition on phi1, then we can actually solve the, say, problem of endogeneity essentially by, well, fixing with respect to phi1 and then doing actually our quanta regression for fixed levels of v1. Well, then we still have to formally prove, and actually that is the same as saying that conditioning on x1, z1, and v1 makes d1 independent from u1. We should realize that this actually means that at the moment that we are going to condition on x1 and z1. Well, we can always condition x1 and z1 because of the fact that they are observed. We can also, well, condition in this case on v1 because of the fact that we do know that instead we can condition on w1 because of this thing that we say over here. So that means that we can condition on x, z, as well as even on v, and that makes actually d1 completely deterministic, and therefore it does not add any information for the shape of the distribution of u1. But that's the thing that we still have to prove as well, but let's start actually with the first thing to prove, and that is that conditioning on w1 is the same as conditioning on v1. Well, how can we do that? Well, the first thing that I'm going to do here is that I'm going to first of all look at the distribution function of d1 condition on x1 and z1. And I'm now not going to, like here, going to, well, evaluate it in the random d1, x1, and z1, but instead I'm simply going to evaluate this in, say, given numbers. I denote them here by d, x, and z. That's usually what we do at the moment that we're going to look at distribution functions. We do not evaluate them in random numbers, but we evaluate them in just given numbers as we do over here. What is this over here? Well, that's of course equal to the probability that di is smaller or equal to t, condition on x1 equal to x, and z1 equal to z. And then the next thing that I can do is that I can now use the definition of di. That's of course equal to, well, that we already know, that is equal to gamma 0 v1 plus gamma 1 v1 x1 plus gamma 2 v1 times z1. Then I can realize that this x1 of course is exactly equal to that x1 live over there. That one's equal to 2 little x. So therefore this is also equal to little x, and we can do exactly the same thing with respect to z1. That's equal to that z1 equal to z. So therefore also this z over here. So then we get this relationship over here. Then the next step that I'm going to take is that I know from actually slide number 3 that, well, this thing that we have over here, the, say, right hand side of the d equation, that we usually can denote as the function h, x, z, and v1. So therefore I'm actually going to write it like this. This was just a definition. The right hand side of the d equation was given to be possible to write as h, x, z, v1. Now we should realize that because of the fact that we condition x1 and z1, we have here just deterministic numbers, so the only thing stochastic we have over here is v1. And then we have made this assumption that, well, this function h is strictly increasing in its third argument, in this v1 that we have over here. That means, of course, what we can do is that we can take inverses with respect to h1 or h at the left and right hand side. If I'm going to do that, then I'm only going to have v1 here at the left hand side, and at the right hand side I'm going to get the inverse function of h evaluated in x, z, and d. Well, now I can realize that v1 is of course independent from x1 and z1. That's by assumption. That's also on this third slide. And then finally we now have this relationship over here, and we do know that the distribution function of v1 is actually uniform. So that means that we do already know that uniform distribution, at the moment that you, for example, well, evaluate a uniform distribution in say some value of v, small v, then it's actually v itself. So in this case we evaluated h minus 1 x, z, and d. So this thing is simply equal to h minus 1 x, z, and d. Well, that's going to help us to look at our control function. We do already know that our control function is equal to w1 is equal to the distribution function of d1, well, conditional on x1 and z1. Well, that's exactly the same as what we have over here, of course. So the only thing that I need to get in order to get this thing over here is to replace the small x and z and d by, well, the stochastic x1, z1, and d1. So therefore I can write it like this. And then the next thing that I can do is that I can now realize that, well, d1, what is d1 actually? Well, d1 is by definition equal to h evaluated in x1, z1, and well, V1. That's the definition of D1, or actually better to say, the definition of H. Now we should realize that what we have over here is that we have the inverse function of H, evaluate, take into account that this is the inverse with respect to the third argument, evaluating H itself. So this whole thing is actually nothing else as the third argument that we have over here with respect to the H function, and that is simply equal to V1. So that means now that we have proven that W1 and V1, they are exactly identical to each other. This was a lot of mathematics, but we should take into account that this is actually quite intuitive. It's actually not that difficult to understand that this actually is true. And the reason behind that is that we could actually realize what, well, first of all, what is W1? Well, W1, actually we can calculate W1 for every individual if we know the distribution function. We can of course calculate W1 for every individual that we have in our data set. This of course, well, this W, of course this relationship holds true for the first observation that we have. But we can of course also look at W2 for the second observation. Then we simply are going to substitute in here D2, X2 and Z2. And we can do it for any observation that we have in our data set. And then at the moment that we do something like that, well then we should realize what is then the interpretation of any kind of W that we have for a particular individual in our data set. Well, suppose for example that we have a particular person that has a W equal to say 0.50. What is that? Well, that actually means nothing else is that among the individuals that are exactly identical to that particular individual that have the same X1 and Z1, well, 50% of the individuals have a higher level of D1 and exactly 50% of these individuals have a lower level of D1. So for example, at the moment that we again are going to look at schooling and education, then a W1 exactly equal to 0.5 means that 50% of the observations of individuals that are exactly identical to that particular individual, so in terms of X1 and Z1, so in terms of the observed characteristics, well, 50% have a higher level of D1, so a higher education level, and 50% have a lower level of education. And we should take into account that this, of course, is going to be, well, it's going to be different at the moment that, for example, this W is going to be equal to 0.75, because like what we have with respect to 0.50, well, a 0.75 means that an individual, then we are going to have an individual that among all the individuals that are identical to this particular individual, only 25% of the individuals are going to have, say, a D1 or an education level that is higher, and 75% of the individuals are going to have it lower. And well, we should realize that the ranking should actually be exactly the same with respect to W1 as what we have with respect to V1. In order to explain that, well, it is another time very good to go back to this slide that we have over here. We should realize that at the moment that we're going to fix X and Z, well, then the only variation that we have with respect to D is in terms of V. So individuals can only have a higher level of D at the moment that their V is going to be higher among the individuals that have exactly the same level of X and Z. And that means, of course, because of the fact that we have made this assumption of, say, that this function here, this hxzv, so the right-hand side, is going to be increasing in terms of V, that means, of course, that a higher level of D means a higher level of V. So that means that the ranking that we have with respect to D among the individuals that are exactly identical, that have exactly the same level of X and Z, should be exactly the same as the ranking that we have with respect to V. Now you should realize that V in this case is uniformly distributed, and that means, of course, that the ranking of D should be exactly the same as the, well, V itself. And we should now realize that what do we actually do at the moment that we're going to look at the distribution function of D condition on x and z? Well, that's actually nothing else as the ranking. It's, well, how many percentage is going to be higher or lower than you given the x and the z. So that implies that D and V, they should be, the ranking of D, so the distribution of the condition on x and z, they should actually be the same as the V that we have over here. So that's the first thing that we have now, well, proven, that conditioning on W1 is the same as conditioning on V, simply because of the fact that W1 and V1 are identical to each other. But we still have to prove the second part over here, namely that conditioning on x, Z1 and V1 makes D1 independent from U. Well, that's the thing that we still have to prove. Well, that's actually proven over here. But before I'm going to do that, maybe a good thing to do is that to first of all ask ourselves the question, what do we actually have to prove? Well, what we have to prove is that the probability that ui smaller or equal to u conditional on x, d, and v must be equal to the probability that ui smaller or equal to u conditional on x and v. Well, that is actually proven over here. What we can do is that we first of all are able to rewrite this probability that we have over here as follows. What we can do is that we can first of all condition on the values of z. So we can condition on a value of zi equal to some random or some z that we have over here. That's of course allowed. Well, that is of course allowed because of the fact that u and z, they are independent from each other. And therefore we can always condition on a particular level z. If you don't believe me, well then what you can do is that you can also go the other way around. At the moment that u and z, they are independent from each other, then we can always get rid of z over here, and then we go to be back over here. Well, then the next thing that I'm going to do is that I'm now going to realize that I can use here the definition of di. Di is of course equal to gamma 0 vi plus gamma 1 vi xi plus gamma 2 vi times zi. And then the next step is that I'm going to realize that this xi that we have over here is exactly the same xi that we have over there. That one is equal to little x, so therefore this thing is also equal to little x. But we can do exactly the same thing with respect to the z, that's equal to little z, and v that we have over here, that is equal to the little v that we have over there. And now we should realize in exactly the same way as what we also had for the linear regression model. Most things here are exactly in line with the proof of the linear regression model. Well, we can here realize that we here condition on something which is completely deterministic. Well, we should realize that a random variable can never be dependent on something which is deterministic. So therefore, we can get rid of this part that we have over here. And then the final thing that we only have to do right now is that we have to realize that, well, z again is not going to be dependent on u. So therefore, we can get rid of the z over here. And here we have really proven the thing that we wanted to prove over there. Well, now that we actually have proven everything which was necessary, now the question arises, how are we going to estimate this? Well, we're going to estimate this in two different stages. First of all, we're going to estimate w by w hat in the first stage. For that, we have two different opportunities. The first opportunity that we have is to use quantile regression. Remember that quantile regression tries to estimate the inverse distribution functions. So therefore what we can do is to run all kinds of quantile regressions of d on x and z, and then, well, actually invert these quantile regressions. Well, then we are going to get the inverse of the inverse distribution function. That's of course the distribution function itself, and that actually gives us estimators of the wi hat, which was actually the distribution function evaluated in di, xi, and zi. Well, we have already said before, when I was talking about distribution regression, that this is of course possible, but it's much more efficient to immediately estimate the distribution. Well, in this case, of course, with distribution regression. So instead of doing this thing over here, it would be much better actually to run a distribution regression of d on x and z. And the idea, of course, as usual, is that it's going to be a probit. It's going to be a probit on a dummy variable that indicates that di is smaller or equal to d, conditional, on x and z. And then the only thing that we need to do is to predict, in sense, these probits and state that that's, of course, very simple. You just write predict, and then you get our wi hats. Well, then the next thing that we need to do is, in a second stage regression, we're going to estimate the beta coefficients. There are a couple of different opportunities. The first thing that we can do is that we can do, and this is based on a journal Econometrics article published by John in 2009, what we can do is that we can, actually do a quantum regression, simple quantum regression of y on xi and di. But what we're going to do is that we're going to do this for fixed values of wi. In order to explain that, actually the best thing to do is another time to go back to, slide number 2 that we have over here. That's this slide that we have over here. Remember that at a particular moment in time I said that at the moment that we're going to fix the values of vi, for example vi equal to a half, then we have solved, in fact, the endogeneity problem, because of the fact that then d and u, they are no longer correlated to each other. Well, based on that idea, what we can do is that we can simply run a, say, quantum regression, fixing the levels of v. Well, we are actually going to do that by fixing the levels of wi. Well, better to say we're going to fix the levels of wi hat. So for, say, values in our data set for which wi hat is always the same, we're going to do a quantum regression. So in practice that means that, for example, we're going to say let's look at wi hat equal to half. Then what we can do is that we're going to only use those observations in our total data set for which wi hat is equal to half, and then we're going to, based on that data set, run a simple quantum regression of y on x and di. That will give us, say, consistent estimators of beta 0, beta 1, and beta 2. However, there's only one problem with respect to this, and that is the problem that we should realize that vi and hence wi, they are continuously distributed. So that means that we are not going to observe that many wi hats which are going to be exactly equal to half. A solution to that is that what we could do is that we could use similar values. So instead of just using the observations for which wi hat is exactly equal to half, we can use an interval, for example, from 0.4 until 0.6. So we're only going to use the observations in between 0.4 and 0.6. Well, then what we are going to have is that we could, of course, do that even better. We can reduce, of course, the interval to 0.45 and 0.55, or 0.49 and 0.51. Well, what we should do is that we should take this interval as small as possible, of course, based on the number of observations that we have. If we make the interval too small, of course, then the problem that we have is that we have too little observations. But if we make it too large, for example, equal to from 0.4 to 0.6, or maybe even make it larger from 0.3 to 0.7, then we should realize that within our sample, we still have variation with respect to wi and hence with respect to vi. And that means, of course, that still within our sample, we are going to have, say, variation or correlation between ui and di. Only at the moment that we are going to, in the limit, make the interval equal to zero length, then at that moment in time we're going to get consistent estimators. So therefore what we should actually do is to, at the moment that the sample size becomes larger, we should make our interval smaller and smaller. Well, that we can actually do with respect to what we call kernels, but because of the fact that kernels is a part of machine learning, and I'm not going to talk about that over here, I will not say too much about that. An alternative is actually much simpler. And that is that what we could do instead of doing all this that we have over here, we could also do more or less the same thing as what we already did with respect to the standard linear regression model. Remember that in the standard linear regression model, we estimated y on x, d, and an estimator of v I hat. Well, that we can do here as well. Then we actually already correct for the impact that v actually has. Then we actually take already v into account. Well, that we can do here as well. We can simply run a quantile regression of y on xi, di, and wi hat. Now the only problem is that we actually do not know how wi hat, or maybe better to say v, is going to enter the outcome equation. It is going to enter in a certain way, but we do not know actually how it enters. So therefore it's better to be a little bit more flexible, not just to only include wi hat, but to also include, for example, wi hat squared, or wi hat to the power of 3. And we could even use interrelationships between wi hat and xi and di. Well, it's not that easy to actually know which, say, specification is going to be the best, but also here machine learning techniques can actually help you. I would like now to go on with an application, and the application that I would like to look at is about the paper of Engrist and Kruger 1991 published in the Quarterly Journal of Economics. And this is actually not my own application, but it's actually from a paper published by John that I already talked about. It's a paper published in Journal of Econometrics in 2009. But first, something about the Engrist and Kruger paper. Well, this is actually one of the most famous papers, you could actually say infamous papers, in labor economics. What they try to do in this paper is that they try to estimate the returns to education. And we do, of course, know that the estimation of the returns to education is very, very hard. And the reason behind that is because of the fact that education is endogenous. And that means that the standard ordinary squares of, hourly wages on the level of education, and maybe a lot of other things, is going to give us inconsistent estimators. In order to solve this, Engrist and Kruger, they use instrumental variable estimation, so IV. And the instrument that they use is the quarter of birth in a particular year. The question, of course, arises, how is the quarter of birth related to your education level? Well, the answer to that is that is related to the laws with respect to education that you have in the United States. Actually, in the United States, at least in the period that they analyzed, it was possible to drop out of high school in the year in which you turn 16. So suppose that you're born in 1950, that means that in 1966 you're allowed to drop out of high school. Question arises, how old are you then in that particular moment in time? Well, that depends a lot on when you were actually born during the year. Suppose that you're born in 1950, but in the very last days of 1950, say December the 30th or December the 31st. Well, then it of course means that you turn 15, say in 1965, and then the next day it's 1966, and then you're allowed to drop out of high school. So that means, of course, that you just turned 15 and you're allowed to drop out of high school. That's of course quite different from a situation in which you're born in, say, the first days of January, say January the 1st or January the 2nd. Then actually you're going to turn 16 at the moment that you're allowed to drop out of high school. There is 1 year difference in between, say, the possibility to drop out of high school between these individuals. Well, that of course may have an impact on the level of education, because of the fact that if you're allowed to drop out of high school earlier, then your education level may be lower, because of the fact that these are teenagers. They may just decide to drop out of high school at the moment that they're allowed to do so. So that implies that we may expect that people that are born at the end of the year have lower levels of education than individuals that are born at the beginning of the year. And then if you assume also that this thing is not related to the talents that individuals have, so individuals that are born in the beginning of the year don't have better talents than those that are born at the end of the year, well, then you actually have a very good instrument. And this was the reason why a lot of people just after the publication of this article actually had the idea that this was the best article in terms of trying to estimate the returns to education. However, after that, a lot of people realized that this might not be such a great idea. And the reason behind that is because of the fact that the relationship between education and the quarter of birth may actually be very weak. And that implies that you might actually have a so-called weak instrument. There have been many publications that actually say that this relationship results in a weak instrument. And the problem with respect to weak instruments is that then standard econometrics or standard econometric inference is not allowed anymore. Then you have to do something else. And there have been many papers that actually show that then actually the results of Enquist and Kruger, they're completely uninformative. So what they will estimate is a return to education somewhere in between 10 and 15%. That's their point estimator, but the confidence intervals, if you do proper econometric analysis, are going to become very wide, from negative up till say 50%. So that's completely uninformative. So therefore, nowadays people have the idea that you should not use these kind of instruments. And the reason behind that is because of the fact that you should realize that dropping out of high school, even in the say 60s and 70s, where Enquist and Kruger are looking at, meant that you are really at the bottom of the say educational distribution. You're really at the bottom of the people that are say low educated. Most people have a higher level of education, therefore you should realize that for many people these dropout laws are not that important. For people that want to at least have high school or even have some college, the moment that you're allowed to drop out of high school is not that relevant, of course. But this may not be the case for individuals that are really at the bottom of the, say, educational distribution. For people really at the bottom of the educational distribution, at the moment that you already had difficulties of getting through elementary school and middle school, then at the moment that you're in high school and you turn, say, 15 or 16 and you have the opportunity to drop out of high school, then you will actually do that. And then whether you can do that at the age of 15 or at the age of 16 or almost 16 actually matters, and therefore it matters whether you're born in the beginning of the year or at the end of the year. So therefore you might expect that this instrument, even though it's maybe not that strong at the top of the distribution and actually generally is not that strong, it may be very strong at the bottom of the educational distribution. And that's exactly what John actually shows. He shows that even though at the top of the distribution there is no relationship between your education level and say these dropout laws, or maybe better to say the quarter of birth, but at the bottom of the distribution, essentially at tau equal to 0.2, he finds a very strong relationship between the quarter of birth and the education level of the individuals.